Imagine stepping onto a world that is less a planet and more a tantrum with a crust. The moment Earth was born, it did not glide gracefully into existence like some serene celestial swan. No, it arrived loud, fiery, and covered in molten chaos, the cosmic equivalent of a newborn yelling its lungs out. If Earth had a birth photo, it would probably violate several safety guidelines for excessive brightness. Everywhere you looked, the surface glowed with the deep roiling red of liquid rock, churning and stretching like a giant pot of magma stew that had been left on the cosmic stove for far too long. You would not be able to stand here, of course, unless you personally identified as fireproof. The ground was a suggestion, the air was a warning, and the entire planet felt like a lava-flavored smoothie blended at maximum speed. Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing, but only if you enjoy these calm journeys through the universe. Now, let's begin. But imagining this scene is part of the fun. So picture yourself hovering, because standing is definitely off the table, just above the swirling surface of newborn Earth, gazing across a landscape with absolutely zero chill. The heat rising from below would be so intense it could melt your sense of dignity, and the light from the molten surface would flicker and pulse like the planet itself was breathing fire. This was Earth's grand opening performance, and subtlety was not invited. If planets had personalities, early Earths would have been labeled overly dramatic and prone to explosive outbursts. Above this blistering world, the sky would not resemble anything you've ever seen. There would be no blue, no clouds drifting lazily along, no gentle atmosphere hugging the surface. Instead, the air was thick with vaporized rock, minerals broken down into particles so small they danced like cosmic dust motes in the glow of the molten ground. The sky would shimmer with metallic tones, an ever-changing tapestry of reds, golds, and shadows, turning the planet into a living forge. Even your sense of direction would struggle in a world that seemed to be both glowing and smoking from every inch. Hover a little higher, your imaginary protective bubble taking the hint that altitude equals survival, and you would see Earth's surface in relentless motion. Rivers of molten rock snaked across the landscape, branching and converging in unpredictable patterns, like the planet was doodling with fire. Bubbles of trapped gases burst through the magma, releasing plumes of vapor so hot they could cook your thoughts. If you listened closely, again through your imaginary protective shield, you might hear the deep rumbling of the young planet shifting and reshaping itself, a low, thunderous sound like a drumbeat trapped inside the world's core. The entire planet groaned and crackled, as if it were irritated to have just come into existence and needed a moment to compose itself. Night and day did not bring much change here. When darkness fell, the planet didn't become cooler or calmer, it simply glowed even more dramatically. Imagine a world where the continents, or what would eventually become continents, acted like giant nightlights from the underworld. The molten landscape emitted its own eerie illumination, turning the darkness into a stage lit by the crimson heartbeat of a world still deciding what it wanted to be. The stars above would appear faint, almost shy, against the blazing spectacle below. And yet, despite the violence, the noise, and the molten mood swings, there was something breathtakingly beautiful about this newborn Earth. It was raw, untamed, and powerful in ways we can barely imagine today. This was the first chapter in a very long story. The messy beginning required for everything familiar to us to eventually exist. Every mountain, every ocean, every leaf and feather and heartbeat in Earth's future began with this primordial chaos. The sheer intensity of it all was part of the planet's transformation, a necessary act in the universe's grand theater. Even though we could never survive here, imagining this world gives us a strange sense of connection. It reminds us that Earth was not always the calm, blue marble we admire from space today. It had a wild youth, a temperamental childhood filled with fire and fury. The planet we know, the home that feels stable under our feet, is the result of billions of years of cooling, reshaping, and evolving from this nearly unrecognizable beginning. In a way, Earth's early days were proof that even the most chaotic, overheated mess can eventually grow into something extraordinary. And maybe, just maybe, when the universe looked at newborn Earth throwing its lava tantrum, it thought, this one has potential. To understand Earth's arrival, you have to step even further back in time. Before the molten tantrums, before the glowing landscapes, before anything remotely resembling a planet existed. Picture the solar system not as the elegant, orderly neighborhood it eventually became, but as a chaotic cloud of dust and gas, doing its best impression of a cosmic blender. This swirling mass, called the solar nebula, was the leftover material from the birth of the sun. Think of it as the cosmic after-party mess that someone, gravity in this case, had to clean up. And gravity did not do this gently. No, gravity acted like a referee in a food fight, trying to gather everything into teams, but somehow making the chaos 10 times worse. Inside this enormous spinning cloud, particles of dust and bits of rock floated freely, bumping into each other like distracted shoppers in a crowded market aisle. At first, these collisions were soft, the kind of impacts so gentle you could miss them if you blinked. Grain stuck to grain, pebble stuck to pebble, and before long, these tiny clusters began to grow into larger clumps. There were no fireworks yet, just the slow, persistent work of physics, like the universe knitting a planet one stitch at a time. But as these clumps grew, so did their determination. More mass meant more gravitational pull, and more pull meant faster collisions. Suddenly, the gentle cosmic shopping mall turned into a demolition derby with no brakes. Everywhere you looked, rocks the size of houses slammed into boulders the size of mountains, sending shards spinning into the darkness. Larger bodies collided with even larger ones, merging into hot, newly formed planetary seeds called planetesimals. These were the universe's first attempts at making planets, rough drafts, awkward prototypes that were constantly being smashed apart and reassembled. If Earth had a family tree, it would look like a collection of broken rocks taped together with the note, "Work in Progress," scribbled across it. These planetesimals orbited the young sun, jockeying for position like contestants in a race where the prize was becoming a fully formed world. And gravity, ever the chaotic referee, was not playing favorites. Some planetesimals were flung out of the solar system entirely, banished like unruly guests who overstayed their welcome. Others crashed into each other so violently they vaporized on impact, adding even more dust to the swirling nebula. But a few, just a select few, grew larger, more stable, and more influential. One of those seeds was destined to become Earth. As this future Earth gathered more material, it began to heat from within. Every collision delivered a burst of energy, and with impacts happening constantly, the growing planet warmed up like metal being forged in a blacksmith's fire. The interior melted, forming a hot, churning mix of molten rock. Earth was not yet the dramatic, glowing sphere it would later become, but it was already showing signs of its fiery personality. If planets could talk, Proto-Earth might have said, "I'm not fully cooked yet, but give me a minute." During this chaotic era, nothing resembled the quiet orbits we see today. The early solar system was a crowded, unpredictable mess. Imagine hundreds of growing worlds swirling around a bright young sun, each one trying to claim space and mass for itself. Jupiter was forming not far away, gathering material with the enthusiasm of someone scooping up snacks before anyone else notices. Mars and Venus were developing their own identities, but every one of them, even the giants, had to deal with the ongoing cosmic food fight. Rocks flew everywhere, impacts were constant, and in the midst of all that, Earth kept growing, sweeping up debris like a vacuum cleaner with anger issues. But this violent birth was more than just cosmic chaos. It was also an incredible act of sculpting, the universe shaping raw ingredients into something stable and substantial. As Proto-Earth grew, its gravity strengthened, allowing it to capture even more material. It swallowed smaller planetesimals whole, absorbed fragments of shattered worlds, and added their components to its own forming layers. Iron and nickel sank toward the center to create the core. Lighter materials drifted outward. The blueprint for a differentiated planet was beginning to take shape, even though nothing about the process felt orderly. Through all of this, time stretched on in a way that is hard to imagine. Millions of years passed without pause, and yet every moment was filled with transformation. Earth did not appear in a sudden flash. It was sculpted through immense patience and relentless collision. What we now see as a fully matured planet was once a battered sphere of rock, still learning how to hold itself together. And then, after countless impacts and mergers, something remarkable happened. Earth grew large enough to become a true planetary body, stable in its orbit, strong in its gravitational pull, and undeniably present in the forming solar system. It was still young, still hot, still unpredictable, but it had crossed an important threshold. It was no longer just a clump of rock in a cosmic storm. It was a world in the making. The violent birth of Earth reminds us that even the most stable things in the universe began as chaos held together by determination. And gravity, of course. Always gravity. To understand the magma ocean age of Earth, imagine a world trying very hard to pretend it is soup. Not a comforting soup, mind you, more like the kind of soup that bubbles ominously in a wizard's cauldron right before something unfortunate happens. After Earth gathered enough mass to exist as a full planet, the heat trapped inside did not politely dissipate. Instead, it accumulated, building until the surface transformed into an unbroken sea of molten rock. From space, young Earth would have looked like a glowing ember floating in the darkness, radiating energy with all the subtlety of a forge cranked to maximum heat. If the planet had a welcome sign during this era, it would have read, "Please enjoy your stay. Do not attempt to touch anything." There was no solid ground to speak of. There were no islands, no continents, no reassuring patches of crust you could stand on while pretending everything was normal. The entire surface was a molten landscape, a shimmering, restless ocean made of liquefied minerals. Waves of glowing rock rolled and folded over one another, each movement slow but relentless, like the planet was stirring itself with a very large, very fiery spoon. The color palette was something between bright orange and deep red, with hints of gold where temperatures soared even higher. It was beautiful in the way fireworks are beautiful, wonderful from a distance, terrible if you are standing in the middle of them. Of course, imagining yourself anywhere near this place is an act of creative courage. Even if you were wrapped in the most advanced protective gear imaginable, Earth's magma ocean would melt through your fantasy outfit in seconds. You absolutely could not walk here unless your shoes were forged by a star and endorsed by a volcano. And even then, the planet would probably take that as a challenge. The heat was so intense, it was not just a physical sensation, it was a declaration. The surface temperature was high enough to vaporize rock, reshape landscapes in moments, and glow with a brightness that made the darkness of space seem pale. The ocean of magma was not calm either. It churned constantly, fed by the heat rising from Earth's interior. Deep within the planet, radioactive elements continued to release energy, stirring the mantle like a cosmic mixer set on high. This churning sent plumes of molten material rising upward, only for them to sink again as they cooled slightly. It was a planet-wide cycle of convection, a kind of internal breathing that kept the surface in perpetual motion. Standing above it, even in imagination, you would witness a world that seemed alive, not metaphorically but literally, with every inch in motion. The sky above this fiery ocean was no place of calm either. Hot gases escaped the molten surface in massive pillars, venting into the early atmosphere like steam rushing from a colossal planet-sized pressure cooker. These gases included water vapor, carbon compounds, sulfur-rich fumes, and minerals that had boiled into vapor under the intense heat. Together, they formed a thick, opaque atmosphere with color shifting between copper, charcoal, and bruised violet. The sky would flicker as light from the glowing surface reflected off these swirling layers of gas, creating a constantly shifting dome that felt more like a furnace lid than a sky. The air, if you could call it that, carried the roar of a planet in turmoil. You would hear the rumbling of molten currents sliding beneath the surface, the hiss of vapor shooting into the atmosphere, and the low, resonant growl of a planet releasing heat, as if venting frustrations from its chaotic birth. Earth was loud, unapologetically loud, a world incapable of whispering. Every sound radiated with energy, vibrating through the atmosphere in powerful waves. If you brought a microphone here, it would dissolve before it recorded a single second of audio. Occasionally, sections of the molten ocean would cool just enough to form temporary crust, thin, fragile sheets of rock that floated like delicate rafts on a lake of fire. These rafts did not last long. They cracked, sank, or melted within minutes to hours, swallowed back into the glowing depths below. The planet was practicing the art of crust making, experimenting with brief attempts at solidity, but it had not yet mastered the technique. Watching these fleeting formations was like watching ice crystals appear momentarily on the surface of hot metal before evaporating out of existence. The heat from the magma ocean radiated far into space. Even from a great distance, the young Earth shimmered with thermal energy so intense that it influenced the surrounding environment. For any observer floating high above the planet, perhaps in a hypothetical protective bubble, Earth's glow would be unmistakable, like a lantern burning in the vastness of the early solar system. It was a world in the middle of a transformation, caught in the act of becoming something new. Despite the violence and intensity, this molten chapter was a crucial step in Earth's evolution. The magma ocean helped separate heavy materials from lighter ones, allowing the core, mantle, and future crust to sort themselves into distinct layers. This process would eventually give the planet its structure, shaping everything from magnetic fields to tectonic behavior. The chaotic heat was not just destructive, it was sculpting the blueprint for the world to come. For now, though, Earth was a glowing, molten sphere, a world that existed in a state of breathtaking, terrifying beauty. It was a reminder that the calm, solid ground we take for granted today was forged through unimaginable heat and turmoil. And as the planet churned beneath its shimmering sky, it held within it the promise of continents, oceans, weather, and life, quietly forming beneath a surface that had no intention of calming down anytime soon. To grasp the magnitude of the event that formed our moon, imagine Earth going about its molten business, glowing, churning, steaming like the galaxy's angriest stew pot, when suddenly the solar system decided to introduce a surprise guest. This guest was Theia, a protoplanet roughly the size of Mars, drifting through the early solar system on an orbit that would soon intersect catastrophically with Earth's. If cosmic history had a slow-motion replay function, this would be the moment when a dramatic drum beat rolls in and the narrator says something like, "Everything was peaceful until it wasn't." Theia was not a small pebble or a stray chunk of debris. It was a full world with its own gravity, its own mass, and its own ambitions. And for reasons written in orbital mechanics and cosmic luck, Theia and Earth found themselves on a collision course that neither could avoid. The early solar system had all the coordination of a crowded dance floor in the dark. So when two planetary bodies met, they did not politely sidestep each other. They collided with catastrophic enthusiasm. Picture the scene. Earth, still wrapped in its global magma ocean, swirling with molten currents and volcanic fumes, suddenly sees a massive world approaching. Theia grew larger in the sky, with each passing moment until it dominated the horizon. There was no time to react, no cosmic traffic officer waving warnings. The collision happened with such force that if planets had health bars, Earth's would have plummeted into the blinking red zone. Theia slammed into Earth at an angle, body-checking our planet so violently that both worlds briefly lost any sense of normal shape. If Earth had been trying to maintain composure, this was the moment it absolutely failed. But in classic Earth fashion, it would later pretend everything was fine. The impact unleashed energy on a scale that redefines the word unimaginable. The outer layers of both worlds vaporized instantly, turning rock into superheated gas. Entire mountain-sized chunks were blasted into space, along with molten sprays that arced outward in glowing streaks. The collision zone glowed white, brighter than any volcanic fury Earth had displayed before, lighting up the newborn solar system like a cosmic flare. Shock waves rippled through Earth's interior, rearranging its layers and sending tides of molten rock sloshing across the globe. While the surface was obliterated, Earth did not break apart entirely. Its gravity held strong, dragging much of the debris back toward itself. But not all of it returned. A portion of the material, vaporized rock from Earth and Theia, spread into orbit, forming a fiery halo around the wounded planet. This halo was not a peaceful ring of ice like the ones we admire around Saturn today. It was more like a violent, swirling storm of glowing shrapnel, a mix of molten droplets, vapor clouds, and fragments still hot enough to make the sun squint. Within this chaos, something remarkable began to happen. The debris started to gather. Slowly, gravitational attraction encouraged fragments to clump together, forming larger and larger bodies as they orbited Earth. It was a cosmic recycling project in action. Where most collisions end in destruction, this one had a twist. It would eventually assemble an entirely new celestial companion. The early moon began as a spinning disk of incandescent rubble, a glowing ring of fire that circled Earth like a crown forged from the impact itself. As the debris cooled, droplets condensed into rock. These rocks merged into larger masses, then into a single dominating body. The moon took shape not through peace, but through persistence, a quiet sculpting after the storm. When it finally solidified enough to hold its form, it became a glowing sphere hanging above the battered Earth, a newborn satellite carved from catastrophe. If moons could introduce themselves, this one might have said, "Hi, I'm here because someone forgot to enforce the no running in the solar system rule." Meanwhile, Earth was recovering from the blow, reshaping itself beneath its molten surface. Theia's core likely merged with Earth's own, giving our planet a stronger, more complex interior. The mantle stirred with newfound energy, reorganizing in ways that would influence tectonics, magnetic fields, and atmospheric development for billions of years. In a strange way, Theia did not just strike Earth, it contributed to Earth, adding material that would become part of the planet permanently. The two worlds became one, though not by choice. Above, the moon settled into orbit, initially far closer than it is today. It would have loomed huge in the sky, so enormous that if you were floating in a hypothetical safe bubble above Earth, it would feel less like a moon and more like a celestial neighbor leaning too close over the fence. Over time, it drifted outward. But in those early days, the moon was a bold, brilliant presence, reflecting firelight from Earth's molten surface. This collision was one of the most transformative events in Earth's history. It created the moon, reshaped the planet's interior, and set the stage for the stable rotational tilt that would later allow seasons to exist. Out of sheer violence came balance, and out of destruction came companionship. Earth may have been body-checked by a Mars-sized rock, but it rose from the impact with a new satellite and a new identity, pretending, as always, that this was part of the plan all along. After the moon settled into its newborn orbit and Earth began wobbling towards something resembling stability, the universe looked down, nodded, and said, "All right, now let's really test this planet's patience." What followed was a period so relentless, so chaotic, and so downright unfriendly that it deserves its own cosmic warning label. Scientists call it the era of heavy bombardment, but that name does not quite capture the full flavor of the experience. It was less bombardment and more asteroid monsoon season, the kind where the forecast was always 99% chance of impact and 1% chance of even more impact. Earth, still glowing from its magma-filled adolescence, found itself pelted by space debris of all shapes and sizes. If early Earth had parents, they definitely would have insisted it wear protective gear. Fortunately, the planet already had a natural helmet made of lava, because space rocks at the time had absolutely no chill. Imagine stretching your view high above the young Earth. The planet is still recovering from the collision that formed the moon, its surface reshaping and cooling unevenly. But before it can catch its breath, streaks of light slash through the darkness, asteroids and comets plunging inward like cosmic arrows fired from every direction. Some of these objects were small, the kind that might only carve a temporary dent into Earth's still soft exterior. Others were the size of mountains, capable of causing planet-wide ripples with every collision. And a few were even larger, true bruisers of the early solar system, arriving with the kind of energy release you might expect if a star decided to drop a bowling ball. Each incoming rock carried the signature of the solar system's rough upbringing. To understand why so many of them came barreling toward Earth, you have to picture the early planets and their orbital neighbors still figuring out where they belonged. Jupiter, the biggest kid in class, liked to shove things around with its immense gravity. Saturn did a fair share of nudging as well. Their gravitational tug-of-war sent countless objects ricocheting inward, outward, sideways, basically everywhere except where they were supposed to go. Many of these wanderers ended up heading straight toward Earth, and Earth had no choice but to take each hit with the grace of someone repeatedly struck by falling coconuts. Every impact left its mark. When an asteroid slammed into Earth's surface, the molten landscape erupted in towering fountains of liquid rock, shooting outward in fiery arcs. Craters formed instantly, only to be erased moments later as the magma ocean surged and swallowed them. It was a planet in constant renovation, a surface that refused to stay the same for more than a few hours. The bombardment reshaped Earth again and again, turning the young planet into a geological etch-a-sketch someone kept shaking with dramatic enthusiasm. Some impacts were so powerful they vaporized the asteroid and part of Earth's surface in a single burst. The explosion would send superheated material into space, creating glowing clouds that drifted briefly before falling back to the surface as molten rain. Yes, molten rain. Earth was quite literally experiencing weather events made of liquid rock. If anyone ever complains about today's climate, it is worth kindly reminding them that at least the sky is not throwing fire back at the planet anymore. What made this era even stranger was the variety of objects arriving from the depths of the solar system. Some asteroids were rich in metals, others in minerals, and some comets carried frozen gases and chemical compounds locked in their icy bodies. When these icy wanderers struck the blazing Earth, they vaporized instantly, releasing materials into the atmosphere, where they mixed with the thick gases already swirling above the molten world. Each new arrival added a bit more complexity to the planet's growing chemical library. Earth's surface chemistry was not peaceful, but it was becoming more diverse with every fiery collision. Despite the mayhem, this constant rain of cosmic debris played a surprisingly constructive role. Each impact stirred Earth's layers, mixing them like ingredients in a giant planetary cauldron. Some collisions brought in materials the planet did not originally possess. Others delivered elements that would later prove essential to the formation of oceans, minerals, and even the building blocks of life. If early Earth could speak during this ordeal, it might have shouted, "Stop throwing things at me!" But in quieter moments, maybe it would have admitted that some of these projectiles were unexpectedly helpful. The bombardment also influenced Earth's rotation. With every hit, the planet wobbled a bit, shifted a bit, spun faster or slower depending on where the blow landed. These adjustments were small individually, but significant over time, shaping the rhythm of the planet's days and nights. Meanwhile, heat from the impacts kept the surface from cooling too quickly. Even as the magma ocean began to thicken in places, the asteroid onslaught ensured that no stable crust survived for long. The planet wore its molten armor proudly, glowing defiantly under the constant barrage. And through all this, the moon remained a silent witness. Much closer to Earth than it is today, it too was struck by debris, accumulating scars that remain visible even now. But Earth took the brunt of the hits, a world still learning resilience through sheer necessity. Eventually, after millions of years of cosmic chaos, the bombardment began to slow. The solar system gradually cleared its crowded pathways, and Earth finally experienced moments, brief at first, then longer, without something slamming into its face. Its molten helmet could finally start cooling in peace. But the memory of this era remains etched in the planet's identity. Earth's childhood was not gentle. It was forged in fire, carved by impacts, shaped by debris that refused to mind its own business. And yet, from this turbulent upbringing emerged a planet capable of astonishing calm and beauty. The rain of asteroids may have been merciless, but it set the stage for a world that would one day cradle oceans, continents, and life itself. proving that even the universe's roughest weather can leave behind something extraordinary. After enduring an era where the sky fell on it repeatedly, and asteroids used its surface as a landing pad without permission, Earth finally reached a stage where things began, very cautiously, to calm down. Not calm in the relaxing sense. No one would light a candle and take a bath on early Earth unless they wanted to be instantly vaporized, but calm compared to the cosmic mayhem that came before. As the world's molten surface simmered instead of boiled, a transformation began brewing in the depths of the planet's fiery personality. Earth was about to attempt something ambitious. It would try to grow a crust. Cooling a planet is not unlike trying to cool a pot of bubbling caramel by waving at it from across the room. It takes time, a lot of it, and even then, the surface forms a thin skin, while everything underneath remains one wrong move away from erupting all over again. Yet slowly, steadily, Earth radiated heat into space, with fewer catastrophic impacts shaking its insides. The planet had enough breathing room to release some of the thermal energy that had been trapped since its earliest days. The outermost layers of molten rock began to thicken, gaining the first traces of solidity. Earth, after being a swirling sphere of liquid fury for longer than the human mind can comfortably imagine, was finally getting its first real skin, even if it immediately started cracking like a poorly baked cookie. Picture this moment from above. What had once been a glowing, fluid ocean now shimmered with patches that were slightly darker, slightly duller, the cosmic equivalent of cooled frosting forming streaks across a still warm cake. These patches of proto-crust were fragile, more symbolic than functional, and entirely at the mercy of the magma still churning beneath them. They floated like rafts on a lava sea, shifting and breaking apart as Earth's interior continued its slow-motion dance. But symbolic or not, they marked a dramatic turning point. For the first time in its existence, Earth had places that could be touched, hypothetically, without instantly sinking to the center. As these early crustal fragments expanded, they collided with one another, merged or shattered, depending on the whims of the molten currents below. Some pieces grew large enough to resemble tiny continental seeds, though nothing like the continents we recognize today. These early land masses were unstable and restless, frequently torn apart by underlying convection or pierced by rising plumes of magma that forced their way upward like impatient geysers. In many ways, early crust formation was less like building a floor and more like balancing a mosaic on a trampoline. The atmosphere above the planet played a crucial role too. Thick with gases released from Earth's interior, it helped lock in heat while still allowing some energy to escape into space. As heat radiated away, temperature differences between regions of the planet encouraged variations in the crust's behavior. Some areas cooled faster, developing thicker patches of rock that resisted melting for slightly longer than their surroundings. Other regions, especially those above intense upwellings of molten material, refused to solidify at all. The planet looked mottled and scarred, a patchwork of stability floating on a foundation that absolutely did not agree with the concept of staying still. One of the most dramatic features of this era was the way Earth's crust interacted with the magma beneath. Whenever pressure built up below a newly solidified patch, it would crack open in an instant, releasing fountains of molten rock. These fissures glowed like molten veins streaking across the planet's nascent surface and recycling crust back into liquid form. If someone could have watched this from a safe vantage point, it might have looked like Earth was learning how to breathe fire, exhaling heat and glowing red lines across its darkening skin. Over time, centuries blending into millennia, millennia blending into millions of years, Earth's crust thickened enough that some patches persisted long enough to matter. These early stable surfaces began to form the backbone of future geological structures, though they would later be reshaped, buried, uplifted, or completely reworked by the forces of plate movement. These first pieces of crust represented the start of Earth's long journey toward becoming a planet with landscapes rather than lavascapes. The cooling also changed the behavior of Earth's interior. As the crust grew thicker, heat escaped more slowly from the mantle below, creating feedback cycles of warming and cooling that would eventually drive the earliest hints of tectonic activity. Even in these early days, the crust did not rest. It moved subtly, flexed under pressure, and occasionally split apart to reveal the still molten world inside. The planet's surface was in constant negotiation with its interior, each layer arguing about who was really in control. Chemical differences emerged too. Lighter minerals tended to float upward, becoming part of the crust, while denser materials sank into deeper layers. This sorting process helped define Earth's structure, dividing it into the crust, mantle, and core with a clarity that would shape the planet's behavior for billions of years. Though the crust was thin, fragile, and frequently obliterated by internal forces, its formation represented an enormous leap in planetary maturity. Imagine running your hand, again, hypothetically unless you enjoy instant disintegration, across this early crust. It would be rough, uneven, blisteringly hot, and prone to cracking without warning. Steam hissed from vents, molten rock seeped through fractures, and the ground trembled underfoot. Yet it was ground. That alone was revolutionary. Earth had begun the shift from a world defined by liquid fire to one capable of supporting the solid features that would ultimately give rise to mountains, islands, and eventually the landscapes familiar to us. Though it looked unstable, this crust was the foundation of everything to come. It was Earth's first attempt at holding itself together, the beginning of the surface where oceans would pool and continents would rise. And even though it cracked constantly like a cookie baked by someone who forgot to set a timer, it marked the start of Earth's transformation from a molten experiment into a world with structure, personality, and the potential for future life. This fragile skin would not remain peaceful for long, but it was here, at last, and Earth would never be the same again. Once Earth had managed to grow a crust, an admittedly fragile achievement for a planet with a molten temper, it began preparing for one of its most dramatic transformations, becoming a world with oceans, not puddles, not shallow pools, but vast rolling seas that would one day cradle continents, moderate climates, and serve as the sprawling, swirling cradle for the chemistry of life. But before those oceans could appear in all their blue glory, the planet had to survive something far less peaceful. It had to endure rain, not ordinary rain, not thunderstorms, not even monsoon seasons. We are talking about rain so persistent that if you arrived with an umbrella, it would simply resign from its job and walk away. To appreciate this chapter in Earth's evolution, imagine standing, again in a very protective, highly hypothetical bubble, on that early, newly crusted world. The air around you is thick, almost too dense to see through, filled with gases belched from countless volcanic vents. Water vapor is everywhere, escaping from the interior of the planet with the enthusiasm of steam bursting from a kettle left too long on the stove. For millions of years, this vapor collected above Earth, forming a blanket of dense, humid atmosphere. It was as though the entire planet was exhaling the last remnants of its molten childhood. As Earth continued to cool, very slowly and not without occasional fiery tantrums, the temperature of that atmosphere dropped. Eventually, the steam that had hovered for ages could no longer stay suspended. It needed to fall. And when it did, Earth experienced rainfall on a scale so colossal that every cloudburst in human history would look like a light mist in comparison. The heavens opened in a relentless downpour that did not stop for years, not days, not months, years. If anyone had been there to witness it, they would have had time to ponder their decisions, their future, and the fate of their umbrella before the sky decided to take a break. The rain fell onto a planet still warm enough that some droplets instantly evaporated upon hitting the ground, or what few stable patches of ground existed. But as the surface cooled further, more and more of that water remained. Droplets merged into rivulets. Rivulets carved pathways into the young crust. Pathways deepened into channels, and channels collected into sprawling basins. Steam boiled upward at first, fighting the incoming water like two rival forces locked in a dramatic battle. But gradually, the cooling won. The rain no longer vanished in a puff of vapor the moment it arrived. It stayed, it collected, it began to pool. These early basins were not the neatly shaped oceans we know today. They were irregular depressions formed by the chaotic ups and downs of Earth's crust, places where molten rock had sagged or cooled unevenly, forming natural gathering spots for water. As rain continued to fall, these basins deepened and widened. Rivers formed spontaneously, carving proto-landscapes faster than any modern erosion event could dream of. The young oceans grew not by gentle trickles, but by the steady onslaught of planetary-scale rainfall. Imagine the sound of it, a constant roar of water striking rock, an unending hiss of steam rising where rain met hot surfaces, and the distant rumble of Earth's interior shifting beneath it all. The planet had gone from a world of fire to a world of water almost abruptly. Though the process itself took countless millennia, the transformation was monumental. Earth was beginning to look less like a cosmic furnace and more like a world ready to evolve. Below the surface of these forming oceans, something remarkable was happening. Minerals dissolved from the cooling crust mixed with the accumulating water, changing its composition and enriching it with elements that would later become indispensable to biological processes. Salts leached from rock, gas bubbles rose through the water, and the early ocean's chemistry shifted toward complexity. The seas were not yet the welcoming blue expanses familiar to our eyes. They were likely cloudy, mineral-rich, and strange, but they were oceans nonetheless, the first stable bodies of water Earth had ever known. As the oceans expanded, they began to interact with the atmosphere in profound ways. Rainfall washed gases into the seas, while water vapor evaporated back into the sky. These exchanges created cycles, rudimentary at first, that would someday evolve into the full hydrological dance that governs weather today. The temperature of the planet moderated as oceans absorbed heat, storing it and redistributing it in ways the molten world could never manage. With water came stability, and with stability came the possibility for gentler environments to emerge. Of course, it was not all tranquility. Volcanic eruptions still spewed ash and lava, sometimes boiling patches of newly formed ocean into bubbling cauldrons. Meteor impacts still scarred the surface, flinging water into the atmosphere only for it to fall again as renewed rain. The planet was not done reshaping itself, but through all this, the oceans continued to grow, deepening and widening until they became undeniable features of the landscape. Eventually, Earth transitioned from an endlessly raining world to one where water cycled in a more balanced way. Oceans covered vast regions, while patches of rising crust peaked above the waterline, offering the earliest hints of future continents. The sky cleared just enough to allow light through, illuminating the shimmering surfaces of Earth's first seas. For the first time, the planet reflected sunlight instead of only radiating heat. Earth no longer resembled a glowing ember. It looked, for the first time in its history, like a world with oceans, a world with depth, character, and promise. The birth of the oceans was not a gentle event. It was dramatic, lengthy, messy, and occasionally absurd. But it set the stage for everything that would come next: atmosphere, climate, chemistry, and eventually the spark of life itself. Earth may have reigned so long that even the bravest umbrella would have quit, but when the storm finally eased, the world beneath it had transformed into something astonishing, something ready for the next great chapter of its story. By the time Earth had managed to form oceans and stop the sky from dumping water nonstop, you might imagine things were finally settling into something peaceful. But no, Earth, still young, still moody, and still very much figuring out how to be a planet, had one more dramatic act up its sleeve. The atmosphere, which today is a friendly mixture of oxygen and nitrogen that allows you to enjoy such luxuries as breathing, was in its infancy a very different creature. To call it unpleasant would be an understatement. Breathing here would be like inhaling a dragon's bad mood, thick, acrid, and absolutely guaranteed to make your lungs file a complaint. Imagine standing on early Earth, still in your hypothetical protective bubble, of course, looking upward at a sky so dense with gases that sunlight had to negotiate its way through. The atmosphere wasn't yet the clear blue dome we take for granted. Instead, it was an opaque blanket of volcanic exhalations, a churning mixture of carbon dioxide, sulfur compounds, methane, ammonia, water vapor, and various chemical vapors that escaped from Earth's interior with great enthusiasm. Volcanic vents, fissures, and massive eruptions all contributed to this atmospheric brew, pumping out gases at a rate that would make even the most active modern volcano blush. The sky would have appeared hazy, its color shifting depending on what Earth had most recently belched into the air. Sometimes it might glow an eerie orange, other times a deep purple or smoky gray. The heavy, swirling clouds carried particles that scattered light in strange, unpredictable ways. If you could watch a sunrise, it would look more like the horizon catching fire than the gentle glow we know today. The atmosphere moved like a restless creature, thick enough to hold heat close to the surface and heavy enough that every breeze felt more like a slow, suffocating push of gas than a refreshing gust of wind. Earth's volcanoes were the main architects of this toxic sky. They erupted constantly, not hundreds of years apart like modern eruptions, but sometimes dozens of times within a single millennium. They spewed massive plumes of ash and gas high into the atmosphere, shaping the chemical makeup of the air with every blast. These eruptions were not polite puffs. They were explosive declarations of Earth's still ferocious inner heat. Imagine fountains of molten rock shooting into the air, ash clouds billowing outward like dark thunderheads, and sulfur-rich fumes curling across the sky in waves. Even from a safe vantage point, you could feel the entire atmosphere shift and react with every eruption. One of the dominant players in this early atmosphere was carbon dioxide. With no plants, algae, or biological processes to remove it, carbon dioxide accumulated freely, creating a greenhouse effect so strong it would make a modern climate scientist faint. But this was exactly what Earth needed. With the sun still relatively dim compared to today, the dense carbon dioxide blanket trapped heat like a cosmic thermal jacket, keeping the planet warm enough for liquid water to persist. Without this thick, suffocating sky, the early oceans might have frozen entirely, halting Earth's progress toward becoming a habitable world. Sulfur gases contributed their own brand of drama. Hydrogen sulfide and sulfur dioxide wafted through the atmosphere in quantities that would shut down every school, airport, and human activity today. These gases reacted in the upper atmosphere, forming aerosols that gave the sky its strange, tinted appearance. Occasionally, huge volcanic eruptions would darken the world for months, reducing sunlight so dramatically that the surface seemed trapped in a twilight state. The air would sting, the rain, when it fell, would be acidic, and the overall mood of the planet could best be described as extremely uninviting. Despite its hazards, this early atmosphere played a critical chemical role. It allowed complex reactions to occur both in the air and in the oceans below. Lightning storms, frequent and intense, cracked open molecular bonds, sparking new combinations of gases. Ultraviolet light from the sun filtered through the haze, interacting with atmospheric compounds to generate reactive molecules. While no life yet existed to inhale or exhale, the atmosphere was laying the groundwork for future biological chemistry. It was a laboratory, admittedly a hostile one, where ingredients for later life were being stirred, shuffled, and occasionally zapped with cosmic energy. At the surface, the thick air created an environment that felt heavy and hot. The pressure was greater than what we experience today, and the humidity from constant evaporation and volcanic emissions was immense. Standing near a volcanic vent would be like standing beside an industrial furnace, exhaling poisoned steam. In some places, gases would have pooled near the ground, creating pockets of air so toxic that even your hypothetical protective bubble might reconsider its career choices. Strangely, this hostile atmosphere did something vital for Earth's crust. It kept it from cooling too quickly. The heat trapped near the surface allowed geological processes to stabilize. The crust thickened, the oceans deepened, and gradually the planet became less prone to catastrophic upheaval every few hundred years. The atmosphere may have been dangerous, but it was also essential, like a caretaker who doesn't know the meaning of gentle handling. With each passing age, Earth's interior released fewer volatile gases. The atmosphere slowly shifted, becoming less dominated by volcanic fumes and more influenced by interactions with the oceans below. Rain washed minerals out of the air, dissolving them into the seas and altering the chemistry on both sides of the waterline. The sky cleared little by little, though it was still far from breathable. The planet was preparing for its next transformation, one that would eventually invite life to its surface. But in this chapter of history, the world was still firmly in its do not enter phase. The early toxic atmosphere was a furnace, a shield, a laboratory, and a warning sign all at once. It was harsh, but it was necessary. Earth was not yet ready for life, but it was getting there, one gas molecule at a time. As Earth's toxic atmosphere slowly shifted and the oceans settled into their basins, the planet began experimenting with something it had not yet managed to pull off: long-lasting land. Until now, any hint of solid surface had been temporary, constantly swallowed, melted, or fractured by the simmering interior beneath. But Earth was getting better at cooling itself, reluctantly, unevenly, and with plenty of mood swings, and this new balance allowed an extraordinary transformation to begin. Lightweight crust, rich in buoyant minerals like silica, started to rise above the denser, darker material beneath the oceans. For the first time, Earth was dabbling in continental style, though at this stage the planet behaved like someone rearranging furniture every hour, because nothing ever felt quite right. Imagine drifting above this evolving world during a time when the crust was no longer just a fragile cap, but a dynamic, shifting mosaic. Blocks of lighter rock pushed upward, forming embryonic land masses. These were not continents in the modern sense. No sweeping plains, no mountain ranges, no postcard-ready coastlines. They were rough, stubby, uneven pieces of crust emerging from the ocean like islands that had not yet decided if they truly wanted to exist. The earliest continents were wobbly experiments, constantly tested by the fiery mantle below and the restless oceans around them. These protocontinents formed because portions of Earth's crust melted in different ways. Under the oceans, the crust was denser, rich in iron and magnesium, making it heavier and more prone to sinking back into the mantle. But where pockets of crust melted more thoroughly, they produced lighter, silica-rich rock that behaved more like a buoy than an anchor. This buoyant material thickened over time, piling up until it resisted the pull of the mantle and began rising above sea level. In a sense, Earth was discovering architectural preferences, learning that some materials float better than others. It was like the planet had wandered into a cosmic home improvement store and thought, yes, I'll take the lightweight option. Let's see how this looks. Once these floating blocks of crust rose high enough, they interacted with the surrounding environment in new ways. Rainwater, still mildly acidic thanks to the atmosphere's volcanic flare, washed across the surface, breaking down minerals and carrying them into the oceans. This weathering process not only sculpted the earliest landscapes, but also altered the chemistry of seawater, enriching it with dissolved elements. Waves crashed against the shores, carving edges into the land, while streams etched paths across the developing continents. Even though life did not yet exist on land to witness it, Earth had finally acquired the beginnings of a surface with personality, but stability did not come easily. The mantle below was still lively, sending up plumes of molten rock that bulged the crust and occasionally tore it apart. These early continents cracked like a loaf of bread left too long in the oven. Beautiful in their potential, yet prone to sudden, dramatic fractures. Whole sections could drift apart, collide, or founder back beneath the oceans. Earth's interior heat acted like a restless decorator, constantly rearranging everything, as if the planet could not decide whether it preferred minimalist land masses or dramatic geological clutter. Volcanism was a major player during this era. Lava oozed from fissures or burst from newly formed volcanic centers, adding fresh layers of rock to the emerging continents. These eruptions helped thicken the crust, reinforcing its buoyancy and allowing land masses to survive long enough to grow. With every volcanic outburst, the continents gained height and mass. Though far from tranquil, this period marked the first time land had a fighting chance at permanence. As continents grew, they began interacting with one another in surprisingly complex ways. Just like modern continents, these early land masses drifted on the slow currents of the mantle, though at the time, the drift might have felt more like an unpredictable shuffle. Some proto-continents collided, merging into larger blocks. Others drifted apart, forming smaller, isolated pieces. These collisions were not gentle. When two buoyant crustal bodies slammed together, they crumpled and thickened, forming the earliest hints of mountain-like structure. These were not mountains as we know them. They were more like swollen ridges, but they represented the beginning of Earth's long geological practice of crushing land together to see what happens. Above these rising continents, the atmosphere continued its slow transformation. Weather patterns shifted as land disrupted airflow, creating new temperature gradients and altering how moisture moved around the globe. These subtle changes helped shape erosion, distribution of minerals, and even the temperature stability of the oceans. The continents did not simply sit passively on the surface. They influenced the entire planetary system in ways that would become increasingly important over time. Beneath the continents, another quiet revolution was happening. As the crust thickened, it insulated the mantle below, slowing heat loss and subtly altering the internal movements of the planet. This feedback between continental growth and mantle behavior helped stabilize Earth's geology. The planet was still far from calm. Eruptions, rifting, and collisions remained common, but the cycles became more predictable, more structured, as though Earth finally understood how to pace itself. What makes this chapter remarkable is that continents were not inevitable. A planet could, in theory, remain ocean-covered indefinitely, but Earth's unique blend of chemistry, temperature, and interior dynamics allowed it to rise above the water, literally. The continents would go on to host life, store heat, shape climate, and anchor ecosystems. Yet all of that began with these early, awkward, ever-shifting land masses testing out their ability to persist. In the end, Earth's first stable continents were less about stability and more about persistence. They cracked, drifted, collided, sank, rose again, and repeated the cycle endlessly. But with each iteration, they grew stronger, thicker, and more resilient. These early continents were the planet's first attempt at long-term structure, a kind of geological rehearsal for the grand landscapes that would eventually define the world. Earth might have rearranged its land like someone indecisive with interior design, but from that constant experimentation came the foundations of the continents we know today. And for a planet still fresh out of its fiery adolescence, that was nothing short of extraordinary. Even as continents began tentatively rising from the oceans like shy performers stepping onto a stage, Earth's interior had no intention of letting the surface grow too comfortable. Deep inside the planet, heat was still battling for dominance. Primordial heat left over from Earth's violent formation, heat generated from its slowly cooling iron core, and heat produced by the decay of radioactive elements embedded within its mantle. Together, they created an internal tug-of-war that shaped nearly every feature of the planet's early surface. If the continents hoped for peace and quiet, they were in for disappointment. Earth's interior ran on drama, and it had an impressive habit of announcing itself through volcanic eruptions, which were basically Earth's original social media notifications, loud, frequent, and impossible to ignore. To appreciate the magnitude of this internal struggle, imagine Earth sliced open like a cosmic cross-section. At the center lies the core, a dense, scorching sphere of metal churning with energy. Surrounding it is the mantle, a vast layer of partially molten rock that moves slowly and unevenly, but relentlessly. And sitting on top like a crusty lid is the brittle shell of continents and ocean floors. The heat rising from below does not move in a straight, polite path upward. It twists and heaves, creating currents that push and pull at the crust above. Every ripple in the mantle, every section of rising lava, every sinking slab of cooling rock sends a message upward. The planet is still very much alive. Radioactive elements, uranium, thorium, and potassium among them, added their own twist to the story. As these elements decayed, they released energy, feeding the mantle's churning motions. This process acted like a slow-burning fuel source hidden deep within Earth, keeping its interior hot long after the surface began cooling. Without it, Earth might have solidified into a geologically quiet world early in its history. Instead, radioactive heat kept the planet restless, energetic, and forever eager to remodel itself from the inside out. This internal heat had visible consequences on the young surface. Volcanoes were everywhere, not clustered like modern volcanic arcs, but widespread, unpredictable, and astonishingly frequent. Some erupted gently, letting lava ooze out in glowing rivers that spread across the land. Others exploded with such force that they blasted plumes of ash high into the atmosphere, temporarily dimming sunlight and altering weather patterns. These eruptions were not isolated events. They occurred so often that the landscape was in a perpetual state of renewal. Fresh layers of basalt coated the continents, while older surfaces cracked and folded under the pressure of rising magma. Standing anywhere on early Earth would have felt like living on a furnace plate. Beneath your hypothetical protective bubble, the ground trembled from the constant motion below. Steam vented from cracks. Lava seeped through fissures in slow, molten pulses. Even dormant regions could suddenly awaken as mantle plumes, hot upwellings rising from deep within the planet, punched through the crust and created new volcanic centers. These plumes acted like geological hotspots, generating chains of volcanoes that migrated as the crust drifted overhead. They carved tracks across the planet, leaving behind a trail of igneous scars that spoke to the mantle's relentless energy. The tug-of-war of heat did more than create fiery spectacles. It sculpted the continents themselves. When sections of the crust heated, they expanded and rose. When they cooled, they contracted and sank. These movements created basins, uplifts, and fractures that rearranged the surface over and over. Entire regions could swell upward as mantle plumes pressed against them, only to sink thousands of years later when cooler rock settled beneath. Earth's geology was a living mosaic, forever rearranged by forces that never tired. One of the most dramatic outcomes of this internal push and pull was the creation of rifts, vast cracks that opened in the continents when the mantle pulled in opposite directions. These rifts stretched the land until it fractured, allowing lava to well up and fill the widening gaps. Some rifts were temporary scars, quickly sealed by new rock. Others grew so large that they split proto-continents apart entirely, sending fragments drifting away on newborn ocean floors. In these moments, Earth acted like a sculptor who occasionally got carried away with enthusiasm, reshaping the continents not with gentle brushes, but with forceful strokes of molten stone. At the same time, the crust was cooling slowly from above, stiffening as heat escaped into the atmosphere and eventually into space. This cooling intensified the contrast between the hot interior and the rigid exterior. The greater the difference in temperature, the more the mantle churned, driving the movements of the crust even more vigorously. The continents were passengers on a restless conveyor belt, carried across the mantle's surface like rafts on a subterranean ocean of heat. Earth's volcanic emissions also continued to influence the atmosphere. Gases like carbon dioxide and sulfur dioxide poured from erupting vents, sometimes in such enormous quantities that the composition of the sky changed within geological moments. Each major eruption sent chemical ripple effects through the world's emerging climate systems. And though the atmosphere remained hostile to life, its evolving chemistry was intricately tied to the cycles of heat and cooling below. Even the oceans responded. Volcanic gases interacted with seawater, altering its mineral content and gradually shaping a more complex chemical environment. Through all of this, the Earth maintained a delicate balance. Too much heat, and the crust would melt, erasing nascent continents. Too little heat, and the planet would become geologically stagnant, losing the ability to recycle materials, generate fresh surfaces, and maintain the dynamic interactions that would one day support life. This tug-of-war was not a flaw. It was the mechanism that kept Earth active and evolving. By the end of this chapter in Earth's history, the planet had settled into a rhythm, not a calm one, but a consistent one. Its heartbeat was the steady movement of internal heat, pulsing through the mantle and shaping the world above. Volcanoes erupted, continents shifted, oceans deepened, and the atmosphere thickened and thinned in response. The planet was restless, creative, and endlessly reshaping itself. And though no creatures yet existed to witness the fiery displays lighting up the horizon, Earth was already practicing for a future where its volcanic announcements would whisper hints of its inner workings to life forms curious enough to listen. With continents wobbling into existence and Earth's interior throwing volcanic celebrations on a regular basis, the oceans were quietly becoming something extraordinary. What had begun as endless torrential rain pooling into deep basins was transforming into a vast chemical playground. Every droplet that fell into the sea carried minerals dissolved from the air or leached from freshly formed rocks. Every volcanic vent that erupted underwater delivered new ingredients, and so, while the land above remained restless and fiery, the oceans below settled into a steady simmer of reactions, combinations, and experiments. In these ancient waters, Earth was essentially running a cosmic soup kitchen, stirring, seasoning, and taste-testing the ingredients for something remarkable. To imagine what these early oceans were like, envision a world of cloudy, mineral-rich seas, far from the crisp blue waters we recognize today. Sunlight struggled to penetrate their depths, filtered through an atmosphere still heavy with volcanic fumes. The surface shimmered not just with reflected light, but with chemical complexity, an ever-changing blend of dissolved elements. Water coursed over newly formed continents, carrying sediment and reacting with rocks in ways that altered both land and sea. The oceans were Earth's largest laboratory, constantly fed by rivers, rainfall, hydrothermal vents, and the occasional meteorite that decided to drop in with exotic chemical gifts. One of the defining features of these early oceans was their richness in dissolved ions. Minerals like iron, magnesium, calcium, and silica mixed with water to create a solution ripe for chemical interaction. When rain fell through the atmosphere, it collected carbon dioxide and other gases, forming mild acids that helped break down rocks more efficiently. These reactions released even more minerals into the sea, continuously replenishing the ocean's chemical reserves. The result was a broth of staggering variety, thousands of compounds swirling, bumping, colliding, and forming new molecules in a constant cycle of creation and destruction. Deep beneath the surface, where seawater seeped into cracks in the crust and met magma-heated rock, hydrothermal vents flourished. These vents spewed superheated water rich in metals and minerals, creating plumes of material that drifted upward like underwater smoke. The mixing of extremely hot vent fluids with colder ocean water produced temperature gradients that encouraged chemical reactions. Minerals precipitated out of the solution, forming chimney-like structures around the vents. Towering mineral formations built molecule by molecule. These structures housed microenvironments where reactions could occur at different speeds, temperatures, and concentrations. Think of them as natural test tubes built by geology rather than glass blowers. At the ocean's surface, sunlight provided a different kind of energy. Ultraviolet rays, much stronger in Earth's early days due to the lack of protective ozone, penetrated shallow waters and struck dissolved molecules, breaking them apart or energizing them into new forms. Though harsh, this energy source was crucial. When combined with volcanic heat, geothermal gradients, and lightning storms cracking through the sky above, the ocean was receiving energy inputs from every direction. Each spark, ray, or burst acted as a catalyst, nudging molecules to rearrange, bond, or separate. The result was an ocean alive with chemical possibility. Among the countless reactions happening simultaneously, some began forming more complex organic molecules: carbon, hydrogen, nitrogen, oxygen, sulfur, and phosphorus. The building blocks of life danced through the water in an endless shuffle. Under the right circumstances, carbon-based molecules linked into chains. Nitrogen-bearing compounds formed rings. Fatty acids assembled into primitive membranes. These were tiny, fragile structures, far from anything resembling living cells, but they were steps in the right direction. The oceans were producing ingredients that, given time and the right conditions, could learn to behave in startlingly lifelike ways. Much of this chemical activity occurred near boundaries, places where one environment met another, shores where waves crashed against rock, shallow pools where water evaporated and recondensed, submarine vents where heat met cold. These zones provided contrast, different temperatures, different chemical concentrations, different energy sources. Reactions thrive on contrast, and early Earth excelled at providing it. Molecules drifted into these boundary areas, reacted, shifted, and drifted again. Some broke apart immediately. Others persisted long enough to serve as stepping stones toward ever more complex chemistry. Even the tides, subtle as they were with the moon still orbiting close, played a role. The rhythmic advance and retreat of water allowed reactions to cycle through wet and dry phases, concentrating molecules one moment and dispersing them the next. This oscillation helped drive processes that could not occur in static conditions. The oceans were not just a big pot of water. They were a dynamic system with rhythms and patterns that shaped the reactions happening within. Meanwhile, the atmosphere continued evolving. As volcanic activity gradually shifted and oceans began dissolving atmospheric gases at astonishing rates, the balance of substances in the air changed. This, in turn, altered the chemistry of rain, rivers, and runoff, continually modifying the ocean's composition. The sky and sea were in constant dialogue, exchanging gases and dissolved molecules in a way that made neither environment fully independent of the other. Every shift in the atmosphere affected the ocean, and every reaction in the ocean nudged the atmosphere in return. And through all of this, Earth kept stirring the pot. Heat flows moved water through ocean basins. Currents carried molecules across vast distances. Storms churned the surface. Underwater eruptions injected new compounds. The planet was relentless in its experimentation, running millions of simultaneous chemical trials every second. No living thing yet floated in these waters, no cell yet divided or replicated, but the foundations were being laid with extraordinary precision. The arrival of liquid water's chemistry was not the moment life appeared, but it was the moment the stage was built, lit, and stocked with props. The oceans had become a vast, dynamic cauldron of potential. They were Earth's first great invention after forming land and atmosphere, a world-sized reaction vessel with every ingredient necessary for something extraordinary to emerge. In these ancient seas, Earth wasn't just creating water, it was creating possibilities. And somewhere within that cosmic soup kitchen, a recipe was quietly coming together that would change the planet forever. After ages defined by molten seas, toxic skies, asteroid bruises, volcanic tantrums, and oceans bubbling with chemical ambition, Earth finally began something almost shocking. It started to calm down. Not suddenly. Earth was incapable of sudden tranquility, but gradually, like a once rowdy neighbor who eventually realizes maybe they should stop throwing nightly fireworks shows. For the first time in its turbulent youth, the planet began shifting from relentless upheaval towards something resembling stability. It was the era when Earth, after millions of years of shouting its existence into the void, finally learned to use its inside voice. To appreciate this transformation, imagine watching the planet from afar. The glow that once radiated from Earth's molten surface had faded into softer hues. The continents, though still shifting and cracking, had thickened into structures sturdy enough to endure more than just brief appearances. The oceans, which had previously steamed and thrashed under volcanic bombardment, now stretched across the planet with a sense of permanence. Even the atmosphere, once a choking haze of volcanic gases, had begun settling into layers, with the densest particles falling away and clearer skies appearing in patches like windows opening for the first time. This calming trend began with Earth's heat budget slowly balancing itself. While the interior remained immensely hot, much of the violent energy from its formation had finally dissipated into space. Radioactive decay still provided warmth, but it no longer pushed the planet into constant convulsions. The mantle continued to churn, but with a steadier rhythm. If the earlier mantle movements were like unpredictable waves in a storm, these were more like steady ocean swells, powerful but less chaotic. The crust above responded in kind, cracking less often, drifting more smoothly, and beginning to exhibit the earliest signs of organized plate movement. Volcanic activity did not disappear, far from it, but it became episodic rather than continuous. The planet had upgraded from shouting lava every few minutes to speaking molten sentences only when necessary. Volcanoes still erupted with flare, sending ash clouds skyward and reshaping coastlines. But these outbursts were spaced out enough for the surface to catch its breath, and for the first time, long stretches of land remained intact, uninterrupted by catastrophic geological upheaval. These calmer intervals allowed oceans to lap gently at coastlines instead of boiling away instantly in volcanic rage. The air above began its own transformation. As fewer volcanic plumes entered the atmosphere, the thick layers of ash and gas gradually thinned. Though still far from breathable, the atmosphere became more stable, with clearer regions allowing sunlight to filter through in warm golden bands. Sunlight interacting with water vapor created subtle climatic patterns. Winds strengthened, clouds formed more predictably, and rainfall settled into cycles. Where rain had once been a ceaseless deluge, it now arrived in waves, contributing to erosion in a gentler, more structured way. Rivers carved smoother paths, and sediment began to accumulate in organized layers that would eventually become the rock records geologists love to decipher. Earth's oceans also began participating in the planet's newfound calm. With reduced volcanic bombardment and more stable temperatures, currents started forming. Warm water circulated toward cooler regions, while cold water sank and moved back toward the equator. These early current systems helped distribute heat across the planet more evenly, preventing extreme temperature differences from dominating the landscape. Oceans were no longer just chemical reactors, they became moderators, smoothing out Earth's mood swings like a planetary thermostat. Meanwhile, the continents grew thicker and more coherent. Instead of crumbling apart under constant pressure, they now floated steadily on the mantle like rafts that had finally found their balance. Some collided gently, stitching together into larger land masses. Others drifted apart, but at a pace slow enough to avoid geological carnage. These continental adjustments influenced wind patterns, wave behavior, and even the temperature of the oceans. Though small compared to modern continents, They were beginning to sculpt the world into a more complex and varied environment. In the slower, quieter Earth, erosion took on a starring role. Wind, waves, and rain steadily shaped the surface, smoothing jagged volcanic landscapes into slopes and valleys. Sediment washed from highlands into shallow waters, settling into new layers that would someday be transformed by pressure and time into sedimentary rock. Every grain of sand, every pebble rolling down a stream bed marked the beginning of Earth's long habit of recycling its own materials. For the first time, the planet wasn't just building, it was reorganizing, refining, and maturing. This relative calm also allowed chemical gradients to stabilize across land and sea. Temperatures moderated, salinity levels adjusted, and mineral distributions began forming predictable patterns. These steady conditions were crucial. In the earlier eras, reactions were constantly interrupted by cataclysmic events. Now, reactions could proceed uninterrupted for longer periods, allowing complex molecules to accumulate and persist. The oceans, once dominated by violent mixing, now hosted gentle zones of stillness alongside regions of energetic circulation. These contrasts set the stage for chemical intricacies that would one day tip into biological processes. Even the atmosphere's collaboration with sunlight became more refined. As volcanic haze cleared, ultraviolet radiation interacted with atmospheric gases in consistent ways. These photochemical reactions helped form the earliest hints of protective layers, including the beginnings of the ozone-related processes that would later become essential for shielding life. Though still fragile and incomplete, these changes demonstrated Earth's growing ability to regulate itself instead of letting cosmic forces make all the decisions. Through all of this steadying, the planet developed something it had never possessed before: rhythm. Days and nights brought predictable temperature swings. Winds followed patterns. Rain fell, evaporated, and returned in cycles. The geological outbursts that once defined Earth's personality now accentuated it instead. The world had not become passive, it had become balanced. Energy moved through it in loops rather than explosions. The planet was learning to operate with finesse instead of fury. And perhaps most importantly, this calm created the stability necessary for life's future emergence. Without a quieter world, molecules would have been destroyed faster than they could assemble. But Earth's new inside voice, its gentler oceans, calmer skies, and more predictable heat flow, made room for complexity. It made room for possibility. The slow cooling and calm did not mark the end of Earth's transformation. Rather, it marked the beginning of a world capable of nurturing, a world prepared not just to exist, but to support something fragile, intricate, and astonishing. The universe had built the stage. Earth had settled into its role. The next chapter would bring its first true performers. By the time Earth had eased into its calmer phase, its crust steadier, its oceans deeper, its volcanic outbursts no longer constant background noise, the planet found itself on the brink of something unprecedented. It wasn't life, not yet. Earth was still a few steps away from that remarkable milestone. but the ingredients, arrangements, and environmental moods necessary for life were quietly falling into place. If the planet had been hosting a grand cosmic dinner party, this was the moment when it finished laying out the plates and silverware, arranging the chairs, and dimming the lights. Earth was setting the table long before life arrived to eat. To understand just how monumental this phase was, imagine hovering over the young world at a time when it no longer resembled a disaster movie. The continents, though still more like scattered fragments than fully formed land masses, held their shapes long enough to influence wind and water patterns. The oceans glimmered under sunlight that could finally break through the thinning atmosphere. The skies, still far from breathable, carried fewer volcanic toxins, allowing more consistent sunlight to reach the surface. It was as if someone had turned the cosmic dimmer switch from chaotic inferno to mildly dramatic but livable. The crust had matured into something resilient and varied. Instead of a thin, crack-prone surface constantly flirting with collapse, Earth now boasted areas of thicker, sturdier crust capable of supporting long-term stability. This created a diversity of environments: shorelines, shallow seas, deeper basins, volcanic plains, and rocky plateaus, all exposed to different temperatures, chemical conditions, and levels of sunlight. Diversity is the oxygen of possibilities. With more types of places came more opportunities for chemical complexity to build toward biology. The oceans, too, were evolving. Their temperatures dropped into ranges where delicate molecules could survive for meaningful periods. Currents circulated nutrients efficiently, transporting dissolved minerals from the deep sea to sunlit shallows. Some regions near hydrothermal vents hosted enormous temperature gradients, while other parts remained cool and calm. These contrasts created chemical pockets, tiny universes with their own rules, where complex molecules could develop without being immediately obliterated. The seas were no longer merely a planetary bathtub filled with reactive ingredients. They had become structured and dynamic ecosystems in waiting. Meanwhile, the atmosphere continued its long journey toward moderation. Though still dominated by gases inhospitable to modern lungs, its density had decreased enough that sunlight reached the surface with greater predictability. That sunlight carried energy, steady, dependable energy that could drive reactions essential for pre-life chemistry. Lightning, too, still flashed across the sky, providing surges of electrical energy that jump-started molecular formation in ways calm conditions never could. UV radiation, though powerful, now struck a surface dotted with protective niches, shadowed pools, mineral-lined cracks, underwater shelves, where molecules could absorb energy without disintegrating entirely. Earth was slowly teaching itself to be hospitable. One of the most important developments of this era was chemical stability. Earlier in Earth's story, chaos reigned. Heat, pressure, and impact events tore apart molecules before they could do anything interesting. Now, in contrast, molecules had time to linger. They could float, accumulate, interact, and form more intricate structures. chains of carbon grew longer, rings of atoms became more common, complex organic compounds settled into layers of sediment or clung to mineral surfaces, protected from the more violent moods of the planet. Some environments saw cycles of wetting and drying, first through tidal action, then through evaporation, creating natural concentration chambers where reactions occurred more quickly. These cycles acted as nature's version of a slow cooker, producing chemical richness over long spans of time. Mineral surfaces on land and underwater played a quiet but powerful role. Certain minerals acted like catalysts, encouraging molecules to bond more readily. Others provided physical scaffolding, holding molecules in place so they could interact. Clay particles, metal sulfides, and silica-rich surfaces turned into playgrounds for early chemistry. Earth was offering not just ingredients and energy, but workspaces, natural laboratories carved into rock, sediment, and geothermal structures. Just as important was the planet's thermal moderation. The temperature swings between day and night softened. The oceans no longer boiled away during volcanic tantrums. The crust, insulated from extreme changes, maintained environments that remained stable for thousands of years at a time. In those stable niches, pre-biological chemistry became increasingly intricate, branching into pathways that hinted at the first steps toward metabolism, replication, and compartmentalization. And even the interplay between ocean and atmosphere reached a new level of sophistication. Gases dissolved in seawater, reacted with minerals, and then returned to the air in altered forms. Earth was beginning to run biogeochemical cycles that resembled modern ones in spirit, if not in detail. Carbon circulated, sulfur cycled. Nitrogen began its long, enigmatic journey toward life's future nitrogen fixation strategies. Though no organisms yet managed these cycles, the planet itself flirted with the rhythms that life would eventually formalize. On the continents, still barren, still rocky, new landscapes emerged that could shelter fragile chemical structures. Pools trapped by ridges, tide flats alternately drenched and dried, volcanic fields peppered with cooling lava ponds. These were the quiet corners where molecules could gather, accumulate, and persist. Each microenvironment was like a seedbed waiting for the right combination of ingredients to sprout something unprecedented. Crucially, Earth now provided not just conditions conducive to chemistry, but time. Long spans of relative calm allowed improbable reactions to become inevitable simply through repetition. Molecules that would have been destroyed in earlier ages now had the luxury of attempting new configurations over millions of years. A single successful reaction was meaningless, but trillions of reactions, repeated endlessly across oceans and continents, created probabilities that matter. What defined this chapter was not the appearance of life itself, but the readiness for life to appear. The world had balanced heat with coolness, energy with protection, chemical diversity with environmental consistency. It had crafted oceans brimming with reactive opportunity and skies that delivered just enough power to keep things interesting. Earth had become a place where life was not guaranteed, but entirely possible. If the universe had been watching, and who's to say it wasn't, this would have been the moment it leaned in with anticipation. The planet had prepared itself beautifully. It had arranged its environments, fine-tuned its chemistry, and orchestrated its rhythms. Earth had set the table. Now, all it needed was its first guest. As the long arc of Earth's earliest history curves toward a gentler horizon, it becomes impossible not to marvel at just how dramatically the planet has reinvented itself. To look at Earth today, a calm blue sphere brushed with white clouds and stitched together with green continents, is to witness a world that bears almost no resemblance to its explosive beginnings. The transformation is so complete, so sweeping, that trying to compare newborn Earth to modern Earth feels like comparing a spark to an ocean, a roar to a whisper, a firestorm to a sunrise. If the planet had kept a scrapbook, its first page would be so chaotic, so overheated, and so spectacularly unstable that the rest of the album would look like an entirely different planet's life story. It helps to imagine a split screen. On the left, Day 1 Earth, fresh from its cosmic collision, glowing like a frantic ember. On the right, the world outside your window, calm skies, stable ground, maybe the distant roll of waves or a breeze brushing through leaves. The contrast is almost comical. Early Earth didn't have oceans you could swim in, continents you could stand on, or an atmosphere you could breathe. Instead, it offered molten landscapes, poisonous skies, asteroid barrages, and volcanic tantrums you could time your day around. The modern planet is practically a spa retreat by comparison. The Earth of today hums with moderated energy, its crust thick and cool, its oceans steady, and its skies gentle enough to nurture all forms of life. No one encountering that first incarnation, fresh, fiery, and still figuring out how to be a planet, would ever guess what it would become. Imagine showing someone a before and after picture. The infant Earth, all molten glow and swirling vapor, followed by the tranquil, marble blue world we know. You'd have to reassure them these are not two unrelated planets accidentally placed side by side. In its youth, Earth was a creature of extremes. Even calling it a planet barely did it justice. It was more like a giant, unstable experiment conducted at temperatures that would make a star nod approvingly. The magma oceans churned. Volcanic fountains erupted without pause. The sky flickered with lightning from storms far more dramatic than anything modern meteorologists would dare predict. Earth wasn't just loud, it was spectacularly loud, as though the planet believed the universe only valued volume. But over time, the intensity softened. Collisions ceased, crust formed, oceans settled, the atmosphere thinned and changed. The planet cooled just enough to stop glowing like a warning sign. From that chaos emerged structure. From structure came stability, and from stability came the first whispers of habitability. Earth, once a cosmic fireball, gradually embraced serenity. Not absolute calm, of course, but a far more livable tempo. It mellowed, it matured, it found its balance between hot interior and cool exterior, between restless geology and steady surface, between destructive energy and creative possibility. What makes this transformation feel cinematic is not merely the scale of change, but the way each chapter of Earth's early history set the stage for the next. The violent birth made the core. The magma ocean organized Earth's internal layers. The great collision formed the moon. The asteroid bombardment shaped the crust. Oceans carved landscapes and created chemistry. The toxic atmosphere moderated. Continents stabilized and internal heat found its rhythm. All of it was necessary. All of it was dramatic. And all of it unfolded long before the first living thing ever blinked or even existed to blink. In looking back, it becomes clear that Earth did not simply become habitable by chance. It earned that stability through relentless transformation. Every moment of chaos contributed a piece of the world that would eventually cradle life. The violent early ages, far from being random destruction, were acts of planetary sculpting. Without the molten beginnings, there would be no continents. Without the early atmosphere, no oceans. Without oceans, no chemistry. Without chemistry, no life. Earth had to walk through fire, literally, before it could cool down enough to become a home. And now, billions of years later, the planet wears its calm like a well-tailored suit, hiding the memory of its rowdy youth behind quiet coastlines and soft skies. Yet traces of those early days remain if you know where to look. Volcanoes still echo the planet's fiery core. Earthquakes whisper reminders that the crust still drifts on a living mantle. The moon circles above, its very existence a badge of the chaos that shaped us. The oceans hold the chemical signatures of reactions older than any fossil. Even the continents carry scars of ancient collisions buried deep beneath their surfaces. It is almost poetic that a world born in relentless turbulence would one day host forests, rivers, animals, and humans capable of gazing back through time to reconstruct the story of its beginnings. Earth became not just habitable, but reflective. From its fiery infancy emerged the possibility of curiosity, of understanding, of perspective. If newborn Earth could somehow pose for a baby photo, the result would be unrecognizable today. A glowing sphere of molten rock wrapped in steam and volcanic haze with zero signs of oceans or continents, more cosmic tantrum than planet. And if you placed that picture in a family album next to the serene globe we now know, someone would inevitably ask, "Are you sure this is the same planet?" The only giveaway would be the giant lava tantrum in the background, because that tantrum, wild as it was, is the reason Earth grew into a world capable of life. The planet had a spectacularly dramatic beginning, but from that chaos came everything.